Okay, so since we only got to go through one of these in class, I'm just going to make a video going over a second example of an accumulation function. So this one, the accumulation is starting at -4, so just be aware of that. It doesn't always start at 0, it starts wherever it tells you to. And so if you do the derivative of this, you just get f of x. So g prime is f of x, and then this is our graph of f of x. And I'm just going to, again, go through the whole process here. So first we're going to look for critical points. So g of x has critical points at x equals, and critical points are where the derivative equals 0. And this is the derivative graph. This is f of x, which is g prime. So this derivative equals 0 at -4 and 0. Because derivative equals 0 there. All right, so then we did increasing and decreasing. So g of x is increasing wherever the derivative is positive. So that's above sea level. So that's going to be from 0 to 3 because g prime is positive there. And then g of x is decreasing wherever the derivative is negative. So that's going to be below sea level. So that's going to be from -6 to 0. Because derivative is negative there. And then our relative maximums and minimums, those come from our critical points. So we're going to make a statement about each of the critical points. So -4 and 0. Now at -4, we don't have a change in sign of the derivative. It's staying negative there. So we're going to say g of x has neither a relative maximum or minimum at x equals -4 because g prime does not change sign there. So we have neither a relative maximum or minimum because there's not a sign change in the derivative. Now at 0, we have a change from negative to positive. It goes from below to above. So that means relative minimum. So g of x has a relative minimum at x equals 0 because g prime changes from negative to positive there. Right, and then we have our absolute maximums and minimums, which come from our candidates test. Your candidates are the endpoints and the critical points. So our endpoints are going to be -6 and 3. And then our critical points are -4 and 0. And so just remember you're plugging them into g of x, which is this accumulation function. So our accumulation is beginning right here at -4. And here's where we have to stop and go and find all the areas for all of these shapes. So for this first triangle here, it would be 1/2 base times height. So that is going to be 4, but I'm going to write it as -4 since it's below the x-axis. And then we have a semicircle. Now a whole circle is pi r squared. So a semicircle is 1/2 pi r squared. And this radius is 2. So 2 squared is 4, half of that is 2. It would be 2 pi. Again, I'm going to say -2 pi since it's under the x-axis. All right, and then we've got a little triangle in there, 1/2 base times height. That's going to be worth 1. And then a square is just base times height. So 2 times 2, that's going to be 4. So again, a lot of people like to find all these areas before they even start part A of the problem. You don't really need them until you get here. So whenever you want to find them is fine. So again, remember we're starting our accumulation at -4, which is right here. And so we're going to go from -4 to -6. Now that means we're accumulating backwards. So it's going to be opposite. So that would be +4. If we plug in -4, accumulating from -4 to -4 means you accumulated nothing, so that's 0. From -4 to 0 is this semicircle, so that's -2 pi. And then from -4 to 3, so that's going to be -2 pi plus 5. And then the chart is your justification. You just need to write out the answer. So our absolute maximum is 4 at x equals -6. And our absolute minimum is -2 pi at x equals 0. So that's everything from first derivative test. Now I'm going to move on to second derivative test. This is inflection points. So g of x has inflection points at x equals. Now this is where the derivative, which is what we're looking at, changes from increasing to decreasing or decreasing to increasing. So we're going to have one at -4, we change from increasing to decreasing. And we're going to have one at -2, we change from decreasing to increasing. And that's it. These don't count as inflection points. When it changes to constant like that, that one doesn't count. So just -4 and -2. When it goes to constant, it does not count as an inflection point. And so because g prime changes from increasing to decreasing or decreasing to increasing there. And then concavity, so g of x is concave up wherever the derivative is increasing. So that's going to be -6 to -4 union -2 to 1. Right, so because g prime is increasing there, and then g of x is concave down wherever the derivative is decreasing. So this graph is decreasing -4 to -2. So because g prime is decreasing there. If you want to make a statement about the constant part, so graph of g would not be concave up or concave down at that on that interval, and so that means that the graph is linear on that part. So g of x is linear on, what was it, 1 to 3, because g prime is constant there. And so remember, every time you do a derivative, you go down a degree. So the derivative of something linear is constant. So g of x is linear from 1 to 3 because derivative is constant. And then the last thing I like to do is just take all this information and put it together into a graph, because it's like that's the whole point of finding all this, is you can put it all together. So I would start out by putting on the points that we already found. These are our endpoints and our critical points. And I'm going to have to estimate for the pi ones. -6, 4. And then -4, 0. Now, pi is 3.1415, da, da, da. Let's just pretend it's -3, just rounding for the purposes of this. So that would be -6. It would be -6 and a little bit, but just for the sake of doing this, let's say it's -6. So 0, -6. And then again, say this was -6 and then +5. Again, I'm just rounding pi to be 3. So if you had -6 + 5, that would be -1. So we'll have 3, -1. Again, it would be like -1 and a little bit. And then I'm going to add on to here, I need to do the inflection points as well. So our inflection points were -4 and -2. Now we already did -4. -4 was both a critical point and an inflection point, which is interesting. We had at -4, this derivative equals 0 and changes from increasing to decreasing. So -4 was inflection and critical point. So I'm going to add on -2 to my chart. And then I'm going to do this point as well here at 1. It's not an inflection point, but the graph does change to being linear there. So since there is a change, I'm going to put it on. I'm going to put it on here. So we're accumulating starting at -4. So our accumulation starts at -4. So if we go to -2, from -4 to -2, that's from here to here. So that's half of the semicircle. So that would just be -1 pi. So it's just -pi. which again, I'm going to round, that would be like a roughly -3. So I've got -2, -3. And then if we do 1, again, our accumulation starts at -4. So if we go from -4 to 1, we're going to have -2 pi plus 1. And so that would be roughly -6 plus 1 would be -5. So I've got 1, -5. Again, it would be -5 and a little bit, but close enough. And then we just need to connect the points with the correct concavity. So we want to be concave up from -6 to -4. So this part should be bending upwards. And then we want to be concave down from -4 to -2. So bending downwards. And then concave up again from -2 to 1. So that's all the way to here. So concave up again for this portion. And then linear from 1 to 3. So this should just be straight.